All right. Good morning. We can get started. So good morning. So you probably got the email, my last email, right? So we'll have the test on Wednesday, but for all the exams, we will cover whatever we did till that point, right? So for Wednesday's class, we'll cover whatever was taught till Monday, right? I expect you to keep up with the book, and if there's, I hope the book should be easy to read, because I don't think the book should be very hard to read before you come to class, right? We're supposed to have a surprise quiz, kind of waiting for us to collect enough material so we can actually have a quiz, right? Right? So if you have any questions about anything, let me know. I mean, whatever we covered so far and stuff, right? So do you have any questions in the stuff we covered in the last class? So last class we kind of started the first module, which is talking about processes, right? We are talking about process as the way for the operating system to know when a program is running, way for it to give it resources, way for it to store whatever structure, whatever context it needs to do when it does a context switch. So if it's trying to move from one process to another process, it uses that as a scratch space, what have you, right? The data structure it uses inside is a process control block, which is a large chunk of memory for whatever the operating system needs to use for that, right? And we're going to continue on with that to talk a little bit about how to create processes, how to delete processes, and things of that nature in this lecture before talking about threads, right? So the first notion is the notion of how to create a process. So we need to figure out how to create a process, because once you create a process, the operating system is supposed to hold all the contents on the process control block, right? To create a process, there are slightly different variants of the same concept. Essentially, you create a copy of yourself. You create a clone of yourself, right? And then you have a way to replace yourself with another program, right? So those are the two ways you create a new process. And a particular operating system may call that using one system call. Essentially what happens is, to create a process, you need to have a process. A process can create another process, right? You can't create a process out of thin air. So you have to create a new process through two steps. One is to create a clone of yourself, and then let the clone replace itself with another program, right? The process of cloning is usually done in Unix using a function called fork, which essentially creates an identical copy of your running program. So when you do a fork, we'll see in a little bit what the example program looks like. When you do a fork, it creates the exact copy of the current process, right? And both the processes will start running from the next statement after fork. Both the processes will have all the stuff that was there before the fork happened. So all the variables that they had before the fork would be shared. But everything else after that is separate. So they don't share the contents. They're separate processes by themselves, right? And then the notion of exec would say, if you call exec, it essentially changes you to another program. I see the example in the next slide, right? So that's a way for you to create a process. So that means you always create the sort of a tree, right? You call the one which is creating you as a parent and the one that is created as a child. And if you think of that, it's sort of like a binary tree, right? You have to have one root process, which is usually created by the operating system. You cannot do anything with that. It's a special process. And that creates other processes, which create other processes, and so on and so forth. And depending on the operating system, you may decide that the child will inherit some or all resources, right? Because otherwise, so you have to understand what is happening, because after you do a fork, both the parent and the child will have the same copies. But you have to figure out what that sharing means. We'll see some of it as we move along in the class. You don't want it to be unknown, but the specific mechanism depends on the particular operating system, right? The specific mechanism may be, if you have a file open before you do a fork, what happens if both the parent and the child starts to write, right? So that's the creation process. The exit process is the notion of how do you kill a process, right? The process can be killed when you do an exit from your program, right? Which may be exit or underscore exit, depending on how you call that from your program. Essentially, that will clean up all this stuff. It'll clean up the process control block. It'll release all the resources that the process held and give it back to the operating system. It could be, good exit like a exit, or it could be a abort or something where the program exits without the user control, right? Without the user having too much input. So if you do a segmentation violation, then the operating system may give you a warning, but you may have to kill you, right? So there are different ways of exiting, abnormal or normal exit. So essentially, these two would create a new PCB, the process creation, and exit would clean out the process control block. So it can be given to another process. It can be done with another person, right? So to make stuff a little bit clearer, the book has a little example on how to use the fork system called to create a new process, right? This is a very simple program. Essentially, you have a main function, right? You have a PID underscore T, which is a syntactic sugar for what a process is called in a particular operating system. In Unix, it tends to be integer, right? So this is most of the stuff are integer. So this is an integer value. But essentially, that's the name of a new process, right? So in this process, the first line we execute is a fork, right? And then we return whatever fork returns, we put it in the PID. What fork returns is the process ID of the child, right? So if you are the parent, it returns the process ID of the new process. If you are the child, it returns 0 because there's no child. It is a child, right? So that's the only way for you to differentiate between whether you are the parent or child, right? There is not really, even though we call it as a parent and child, there is not really that much of a elevation of what parent can do, what the child can do, right? Both of them can do the same thing. Both of them are co-equal, but you call one a parent, one a child. And the way you differentiate that is when fork returns, it either returns, if it couldn't fork for whatever reason, right, maybe because of a long-term scheduler problem, it'll return an error message. It'll return a -1, in which case you can say the fork failed. Otherwise, if you check for the process ID to be, if it's 0, that means you're the child because you are the child. But for the parent, it returns the process ID of the child, right? And you could use this to kill the process. You can use this to control the child, but not in any special way. I mean, any process can, if you have the privileges, you can kill another process and stuff like that, right? So even though it's called a parent and child, don't think of that as a human kind of like a parent and child where the parent has control over the children, right? The only other way it may happen, the system may do is, the child, when it exits, it may not, so it returns the error code back to the parent. So when you do an exit with a value of -1 or something, that is supposed to be returned to the parent, right? So that's one other way where the parent has some significance. It can get the status of how the child exited, and which can do something with it or it can throw away, right? So in this case, we check for whether it's a parent or a child, right? If PID equals 0, that means you are the child because there's no parent for you. This exec basically says replace the copy of the program with this new program, right? So you create a clone of yourself. The child clone basically says replace myself with this new program, which you read from disk, which is ls in this case. So that's a way for you to create a new process which is different from who you are, right? It doesn't have to do exec. It can do some computation here, but if it does an exec, that means it'll be replaced. So the child would end up doing a list command, whereas the parent would come here and wait for what the list command returned, and then it'll print something in an exit, right? Does that make sense? There are multiple variants of this call depending on the particular operating system, but essentially that's what you tend to do. You create a clone of yourself, and then you replace it with something else. You don't have to replace it. You can run your different program here, and that's just fine, right? The one thing to remember is whatever you did before you did the fork is shared by both the processes, right? So if you had computed some number there before you did the fork, and the value happens to be 4, right? Once you do a fork, both of them will have a copy of that value. Both of them will be able to modify their own copy of the value, but that value will not reflect on the other one, right? So if the parent changes the value from 4 to 5, the child will not see the new value, right? So you essentially create a clone, but the values are not shared anymore, right? Does that make sense? So when you do a fork, you get a copy of all the stuff you had at the moment of the fork, and after that you're on your own. You can modify stuff differently, you can do stuff differently. And that may or may not be okay for your application, right? There are conditions where you don't want that, you want them to continue to share. We'll see some of the primitives in the next few slides. But essentially the fork will create a copy of all the stuff you had, right? Which you are free to modify, but it's not reflected on the other side. You have an entire new copy, right? And this is significant because some of the stuff will come back in terms of optimizing this process, right? The problem here is when you create a copy of all the stuff, if you had lots of resources, if you're using lots of memory, if you're using lots of arrays and stuff, you have to create an entire copy of all the contents, right? And we'll see some optimization later on which don't have to do all that explicit stuff. But essentially you're creating an entire copy of the thing, right? So depending on the operating system, this may mean that if you had a file open before, right, you have to define what it means for the two processes, right? Both of them have the thing open. Both of them should be able to write to it. But how that works, what that matters, depends on the operating system. Because if it's not done right, then you may have things running over each other, right? And it'll be more clearer as we go along on why these things will fail, right? So the notion of the fork is clear, right? So one of the things I mentioned was when you do a copy, when you create a new process, you get a copy of all the contents, but you don't get to modify these things. So if you want these things to be independent, if they don't want to be cooperating with each other, that's a good enough abstraction. But if you want them to sort of fork each other and then want to collaborate, then want to compute something together, right? Can you think of a reason why you would want to do a fork and continue to compute on the same data through two processes? So the example I gave here was you fork and you create another program. You create a fork and then you run a program called ls, right? But is there a reason why you would want to fork but not run something else, but run a different piece of code? Run the same code or what have you, right? Yes?
Something like rendering, which is really parallelizable.
Mm-hmm. So, what's the key?
So that you can run, if you had like multiple processors or multiple cores, you can run at once.
Exactly. So when you create a new process, right, the operating system can give it a processor, right? So if you wanted two processor, because you happen to be in a multiprocessor machine, that's one way to get that, right? So when you do a fork, you are creating two processes, so the operating system has to treat them both equally. So it could give each one of them a different amount of processor. So it's possible that if you have two processors, you may get two processors for the same process, right? You won't be able to share stuff, but if you could, then that's one way to do that, right? So this is a way for you to get more CPU resources, because every time you create a new process, you get a new processor assigned to you, right? The problem is you can't modify whatever in the parent. So some cases it works very nice. So for example, the example you gave, which is rendering something, right? For example, if you want to print some document, you created all the data, right? You're not going to modify it. So you can call the child and say, go ahead and render it, make it ready for the printer, right? Since I created a fork, the operating system will give you a separate processor to modify that, right? And this little child can work along with you, concurrently with you. So if you have two processor machine, it will look like you're working twice as fast as one processor, right? But the challenge here is you can't really share the stuff. So the child cannot modify anything that the parent can know, or the parent cannot modify anything and let the child know, right? So the abstraction you want to create for that is the notion of a shared memory, right? There are two ways of sharing stuff. One is called a shared memory and one is called message passing. But essentially those are designed for two cooperating processes to somehow say, whatever I modify, I want to let the other process know because I don't want to be completely independent, right? So the notion of shared memory is actually you need to get the operating system to help you. We'll see a little bit of that when we talk about the memory. We'll see a lot more of it when we talk about memory stuff. The idea here is somehow you have to say on process A, right, which may be the parent, and process B, some chunk of memory would be shared, right? So that means that the operating system has to get involved, and we'll see why, of course, actually in the third module. But essentially, once it happens, it looks like you'll have one chunk of memory that is set up right, such that if one process writes, the other process will see it, right? And that's a way for both of them to collaborate, because if one writes, the other one sees it, and the other one writes, the other one sees it, right? But you have to be careful on how you do this stuff. You can't just do it without control, because I have to only modify with the process that I have control over, right? I don't want to be able to attach to your process and share stuff with your process unless you give me explicit control, right? So it's not as trivial as me saying, I want this to be shared. We all have to collaborate. We all have to make sure that we have the right privileges and we want to do what you want to do. And we'll also see that this is not a trivial task, because if you don't coordinate what we're doing, this can completely mess us up. I'll give you an example of how this is bad. But essentially, the second module talks about how you deal with that, right? And the answer we use for that is called logs. Essentially, the idea here is if you have a scratch space that we all can operate on, right? Suppose we all sit here and we have one piece of paper that we can use to write a novel, let's say, right? Imagine the problem if there was no coordination, we all can write, right? So you'll write something, you'll write something, you'll write something, you'll write something. We'll overwrite each other, we'll add stuff to each other, you'll have gibberish. So we have to make sure that these things happen in an orderly fashion. And that's a sufficiently large problem that we have a whole module just for that, right? But essentially, this is what you want to do. And so for example here, right? Like, so we're not going to go into detail of how this happens. Suppose we made a buffer shared between two processes, right? Buffer of size buffer, right? Now, buffer size. And we'll see an example of how you may share this stuff, right? The idea of how you share that involves there are two processes, right? One is writing into this buffer, one is reading from this buffer. We'll see more of the same example later on when the bugs in this code is fixed, right? We can't fix them till we go to module 2 because we don't have any way of coordination. But what we're trying to do is we want to make sure that once one process writes something, the other process can read from it, right? They're sharing the same buffer, right? So the example here is one of them is producing, one of them is consuming. This is a producer-consumer problem, which is a very classical problem in operating system, right? The idea here is the producer will produce. He'll keep producing as much as it can, but bounded by the buffer. It cannot produce more than the buffer till the consumer takes it, right? So you want the producer to keep producing up to a certain point, and the consumer to take stuff off the buffer, right? And in equilibrium, producer is producing stuff, and then the consumer is taking stuff off of it. So they're both coordinating through this shared structure where you're sending work from the producer to the consumer through this shared buffer, right? You also need a mechanism, which is not explained here, of what happens if the producer is too fast. If the producer is producing stuff too fast, then you have to make the producer wait till the buffer clears up, right? And you also have to have the same thing for the consumer, right? The consumer may come too fast. It does not have enough work, so it has to wait, right? So without going into all the detail, what you're trying to do is you are using this, the two variables called in and out, right? Which is you're creating this as a circular buffer, right? So in and out are used to keep track of where it is. So the producer keeps track of how far it is using the in, and the consumer takes it based on the out value, right? So you want to keep these two pointers. So if they tend to be further out, that means the producer is full, right? So the producer uses that to figure out how much to do, right? I'm going to leave the example of how you work through this code offline, right? Essentially, it's a circular buffer, right? And And so you use this to keep adding stuff. There's a lot of problems with this because they are both operating on the same variable, so they can run over each other, right? And we need other structures we'll see later. But essentially, you can use something like this to share stuff, and that's a good thing, because otherwise you are left with, I can give you two processors, but those processors cannot really collaborate with each other. That's not a good thing, right? So one is a shared memory abstraction. The next abstraction we'll look at is the notion of a message passing, which is very similar to what you'll see when you take a networking course, right? So here there are two processes. They don't share a memory. They basically create a message and send it to the other process. So they create something, send it to another process. The other process will operate on that, right? So they have a notion of a send and a receive. So sender will send, receiver will receive, right? It's very similar to networking. If you took a networking class, you use sockets and stuff to send these stuff. The difference is in the notion of how do you do some of the operations that you do in sockets. How many of you taken a networking class? Oh, there's a fair amount of people have taken networking class. One of the problems with the send stuff that if you're talking networking classes, I have to know who I'm sending it to, right? So that means I have to have a name, right? In the networking class, you might have studied of machine names like www.nd.edu or something like that. Whereas here, you have to create this notion of a name which matters only within the same operating system, right? So you have to create some name to call these things. So I don't send a message to, I don't know what your process is, so I have to have a name mechanism to say, I want to send it to PowerPoint print render or something. So I need to have this notion of a name. That's, of course, defined by the operating system. That may or may not be known to normal people, but you have to have a way of specifying that, right? The other problem when you deal with the networking stuff is, if the other machine is offline or something, you have some time for somebody to wait and retransmit and so on and so forth. Within an operating system, there is not much of a leeway like that. Right? You don't have infinite buffers and stuff. So you may have to force the other process to be buffer bound. So if you're sending too fast, in the real network, you may be tolerant to do some things. Within a kernel, you're a lot less buffer. So you may expect that when you send a message, the other side has to receive it immediately, or it's lost, right? So there are slight variations in a networking code, but essentially that's just what you try to do, right? And this is one of the abstractions that operating systems like Mac, or the Mach operating system that Mac uses, would use to communicate with each other, right? They call this ports, and they send messages to each processor through ports. It's like a sort of like a mailbox. So if I want to send a message to a rendering process, I send it to the rendering mailbox, and then the renderer would take stuff off of that mailbox, right? So these are two mechanisms for processors to communicate. We're not going into the detail of how they will go, and I think we'll actually talk more about the shared memory in this and the next module, right? So essentially, these kind of stuff gives you some set of a notion of processes, how the operating system represents them internally, how you create them, how you delete them, and how you may share them, right? And of course, all the information about what is being shared, what is not being shared, will have to be stored on the PCB. So the PCB will have to have space for the operating system to keep track of what is being shared and what is not being shared, and so on, right? Does that make sense? So I'm actually going to go to the next chapter, which is the notion of threads, right? The notion of threads used to be not as important just a few years back, but now I don't think there is any possible way you can take operating systems without knowing about threads. The notion of threads says that when you talk about a process, you only had one way of giving a CPU to you. There's only one way of giving a processor to you, unless you do a fork. And when you do a fork, you have to explicitly do the sharing and all those things. But most of the world is going towards multi-core machines, right? If you buy a new machine, it's very hard for you to ask for a single core. It's very hard for you to ask for a single processor, right? So when you have multiple processors, right? How many of you have a desktop which has multiple processors, right? Desktop or laptop, they call them multiple core, right? Actually, very few of you, right? I'm kind of surprised, but I think if you buy a new machine right now, it's very hard for you to look for a single processor, right? So I'm supposing that most of you have a slightly older computer. But right now, it's practically not cost effective for you to buy a single processor, right? And the reasons are entirely hardware oriented. The reasons are you're hitting a wall on how fast you can make things go. So it's not possible for you to make a 4 gigahertz processor, right? But it's much cheaper for you to make two gigahertz processor or two gigahertz core, which is where the market is going. Right? They can't keep this the stuff going faster and faster, but they can add more, right? I think Intel is proposing that within the next few years, they're going to go up to like 40 cores or something. They can keep going as many cores as possible, right? So when you have more cores, you don't have, each core is typically not as fast as the single processor, right? So but you have more cores. So when you write a program, if you want to use all the cores available to you to do your process, you have to have a way of giving all the processes to your process, right? And that's not possible in the traditional model, because when you write a program, you think of it as a straight line of execution, right? So the way you do that is through the notion of a threads, right? Threads is a way for a process to have multiple processors assigned to it, and you expect that the different threads of control to be simultaneously operating within the same process, right? And and the key is the threads will share everything else. Right? When you create a new thread, all the threads within the process share everything else. There's no problem with anything. You can share anything, right? Which may be a good thing or a bad thing. We'll see how it's a bad thing in the next lecture. But you can share whatever you want, right? So conceptually, this is what happens. When you talk about a process, you have a single thread of execution, whatever your code was, whatever you're thinking of executing, right? And it has all these stacks and files and all those things. When you do a fork, you essentially create a new copy of this, right? And then they're both independent. They both have one single thread, and then they can communicate with each other or what have you. The notion of a thread says that you still have the same stuff up there, right? You may have some